Going back to section 2.4, these are the notes, but you have similar examples or similar questions on the homework. So this one says, using the definition, determine whether the function is continuous at x equals 3. Justify the conclusion. So we have a piecewise function. We have two formulas. The first formula is a quadratic. It's negative x squared plus 4. So this is an open down parabola, but it's only a portion of it. It says when x is less than or equal to 3. The second formula, it's a line. It's an increasing line, but it's only a portion of it. This is for x greater than 3. So the three conditions doesn't change. The first one, it says find f of 3. And so look at the domain for each one. Which one has the 3? Which one includes the 3? The first one. So I'm going to plug in the 3 into the first formula, and that is negative 5. So this is defined. That's good. I go to the next condition. The next condition is the limit as x approaches 3. But this is a piecewise function. So in this case, we need to find the limit of the function as x approaches 3 from the left. And so look at the domains. The one that is approaching 3 from the left is the first formula. This one is coming from the left side, so you have to use the first formula. And then later, we have to look for the limit of the function as x approaches 3 from the right side. From the right side is the second formula that is coming from the right side, so you have to use the second formula. Remember, first try direct substitution. If you get a real number, then that's the limit. Direct substitution means just plug in the 3 here. So this is basically a negative 3 squared plus 4, which is negative 5. And over here, direct substitution, plug in the 3. 4 times 3 minus 8, that is 4. Are those two numbers matching? The answer is no. So we say the limit of the function as x approaches 3 does not exist. So at this point, the second condition doesn't satisfy. So we say f of x is not continuous at x equals 3, since the limit does not exist. Example 2, similar. It says, using the definition, determine if the function is continuous at x equals 0. So you have a piecewise function. It says, the first formula, we use sine of x over x for any x value except 0. And then the second formula, it says, when x is equal to 0, the y is 1. So first, step 1, find f of 0. Which one includes the 0? Which of the domains includes the 0? This one. F of 0 is 1. This is good. It's defined. So we go to the next step. In this case, we don't do what we did in the previous example. We don't look for the limit as x approaches 0 from the left and from the right. Since the first formula, this one, notice how it includes all the values except 0. So that's the one that we're going to be using. The limit of sine of x over x as x approaches 0. Direct substitution. Sine of 0 is 0, and then the bottom is 0. So 0 over 0, that's not good. Go back to your previous lesson, section 2.3. So this is our lesson 2.3. Let's go to the last page. See the special trig limits? The second one, it's exactly the second one. It says the limit of sine of theta over theta as theta approaches 0 equals to 1. It's exactly what we have. So in this case, the limit is 1. It exists. The third condition, check, are those two values matching? Is this and this matching? Yes, it's matching. So the third condition satisfied. The limit of the function as x approaches 0 equals f of 0. So f of x is continuous at x equals 0. The three types of discontinuity that we have is removable discontinuity, jump discontinuity, and infinite discontinuity. Removable discontinuity, it says, this is when the function has a hole at a point. So we're talking about the function, the graph itself has a hole, but the limit of the function exists and is equal to the value that the function would have at that point if it were defined. So it says, removable discontinuity, it's a graph with a hole in it. So this here, this doesn't matter. This is not part of the definition of removable discontinuity. You may or may not have a closed circle, but what you have is a graph with a hole in it, and the limit exists. Jump discontinuity. This is when the function has a jump at a point, a jump in the y values, like this. So it says, meaning that the left and the right limits of the function are not equal. So see how there's a jump in the y values. So the limit from the left and from the right are not equal. This is not jump discontinuity. You have a graph, and maybe it's somewhere here, and the other one is somewhere here. This is not jump discontinuity. Here you have a gap in the x-axis or in the x values. So that's not the same as this here. This is a jump in the y values. And then infinite discontinuity, that's when you have, it says, this is when the function has an asymptote at a point. So we have a vertical asymptote, meaning that the limit of the function does not exist because it approaches infinity or negative infinity. As we approach a from the left side, the graph is approaching infinity. As we approach a from the right side, the graph is approaching negative infinity. Remember, the moment the limit is infinity or negative infinity, we have a vertical asymptote.